All right, so the first question, which of the following definite integrals should be used to find the arc length for the polar equation? All right, so it's arc length and it's two-dimensional. So we would be using the arc length formula. For polar coordinates specifically, and that would be, the formula is written as alpha beta. You can go A to B though. I'm going to write alpha beta. I'm feeling a little saucy right now. And poor quality beta though. I kind of regret drawing that way. But anyway, it's r squared plus dr d theta squared all under the radical d theta. All right. So we have the r. We need the dr d theta. So dr d theta is going to be, well, constant goes to 0, sine of theta goes to cosine of theta. All right. So I would be writing it's a really good looking radical. So I'm just going to copy that one. Honestly, I don't think I'd be able to draw that again if I tried. So do that. The r squared, so 2 plus sine theta squared plus cosine theta squared. Now I got to extend it. Oh, I'm actually fit. All right, well, what do you know? D theta, but I need my bounds, among other things. But, if this were a question where we're simply asking you to state the answer, then I would just, go to Desmos and see what's going on there. But let me see if I can kind of pare down the inside. Now, you can't guarantee that the actual test is going to have, bounds that are taken care of for you, but you can see all the choices here have the same bounds, negative pi to pi. So without even looking at the graph, but we can look at the graph because I already have it up, assuming it doesn't refresh on me. Honestly, I don't know what this is. This is for a different problem. We're looking at something like this. If you do it from negative pi to pi, it seems to close the loop. But if you're not sure, you just dial this back to something short of 3.14, something short of pi, and see if it falls just short of closing the loop. Right? And it does. So we're pretty confident that that's the correct set of bounds. So negative pi to pi. All right. Now, in this case, it didn't matter, but you never know. All right. I don't see this as one of the choices, so let me distribute it out. So 4 plus 4 sine theta plus sine squared theta. I'm just double distributing the 2 plus sine theta plus cosine squared theta, all under that big juicy radical d theta with the bounds, the appropriate bounds, negative pi to pi. Sine squared plus cosine squared is the same as 1. The 1 plus the 4 will give you a 5. So I'd be looking at negative pi to pi, the radical. Now I'll take it. 5 plus 4 sine theta d theta. All right, so I'd just be looking for the choice that's like that. And of course, because apparently when I made this problem up, every practice test is an old test that I just made into a practice test. I usually clean it up a little bit, change some of the instructions around to make it, more practice test-like. But apparently I was feeling like being a jerk at some point when I made this problem, because look at that first choice. That's kind of mean, right? Got the X's in there. Right stuff, but wrong variable. We need this one. Okay, so it would be this choice. All right. Now, if you know enough to dismiss the ones with the X's in it, you made it a 50-50 rather than a 1 in 4 chance. So, I mean, there is if you want to look at it a glass half full, then you can look at it and say, oh, you kind of did us a favor by putting the ones with the X's there, because there's no way those could be the right answer. So that's if you want to give me the benefit of the doubt, I guess. All right. So that's number one. Number two is curvature. Now, this is a nice problem. It's actually a very easy problem, only because the vector value function is linear, right? It doesn't always play out that way, but when it does, if you know that you're dealing with a linear function, you know the curvature is going to be equal to 0. So you already have part C banged out. That's already taken care of. You know the answer is going to be 0, right? It's just a matter of getting the work to align the right way, right? On the final, right, and actually any test, you got to make sure you're using the appropriate techniques. Because if you remember from the unit, there's a bunch of different formulas, but we only went over the one technique, right? So you got to use the technique that we covered in class in order to get full credit, right? So R prime of theta would be my first move here if I'm going to come up with a unit tangent vector at any value t. So that's defined in terms of t, right? So R prime of t is going to be nice and easy because the derivative of a linear function is just that linear function's slope. So 1, 2, and 1/2. So when I made up this test for, I honestly, I believe this is from it was from the fall, right? So I try to balance every instance in which I'm a jerk with one where I'm a nice guy. So number one, I threw the ones with the X's in there. Kind of have your opinion on that, but this one was supposed to be a gift if you knew the appropriate technique, right? Because it's nice and easy to work through. All right. So the derivative is the 1, the 2, the 1/2, just the slopes of the linear components. And I need the magnitudes, or the magnitude, sorry. That's going to be 1 squared plus 2 squared plus 1/2 squared under a radical. And that computation I deleted from Desmos. I think that was before, because I was revising my answer key. I think that's what I actually needed. I really wish I remember what those numbers were. Oh, you know what I could do? There it is. All right, so 1 plus 4 plus 0.25 under a radical. So the square root of 21 over 4 becomes the square root of 21, not something you're going to simplify, be able to, over 2. All right, so that's your magnitude. Now I need the unit tangent vector, t of t, which is going to be each of these entries divided by the corresponding magnitude, divided by the magnitude. So 1 divided by radical 21 over 2 is going to be 2 over radical 21. 2 divided by radical 21 over 2, the same as 2 times 2 over radical 21, so 4 over radical 21. And then 1/2 divided by radical 21 over 2 would be 1/2 times 2 over radical 21, which is going to be 1 over radical 21. All right. So that's part A. All that for a drop of blood. Yeah. So it's really, I mean, when you think about it, compared to some of the other, I was going to say unit tangent vector problems, but really more so the curvature problems. That's not bad. It's not terrible. Part B, it says evaluate it when t is equal to 0. Well, there's no t in my unit tangent vector, so it's going to be the same thing. All right, so there's no change there. All right, and so if you recognize this as a linear function, depending on what the question asks you to do, if this is a show all work kind of question, show all your work in the file upload area, that kind of deal, then you'd have to show the steps. But if it's just a fill in the blank, give me your answers. I mean, you might still choose to show your work, but all I would need is the kappa equals 0. Right? So, but let's assume it's to show all your work. So for part C, I would need T prime of T. Fortunately, they're all constants, so that's going to give us the 0 vector. Pretty nice. All right. We need the magnitude of T prime of T. Doesn't get any nicer than that. Magnitude of the 0 vector is 0. And kappa is the magnitude of the unitangent vector's derivative over the magnitude of the derivative of the vector valued function, which is going to be 0 over the square root of 21 over 2, which is going to be 0. All right. So whether you do it intuitively or if you do it based off of your computations, your algorithmic approach, either way, you should come up with 0 as an answer. So number three starts getting a little dicier because this is one of those kind of questions where, if you had your own choice in the matter, you might decide to go with spherical coordinates, but the question's telling us to go with cylindrical coordinates, right? So we're stuck. We don't have a choice, right? You have to use cylindrical coordinates, or at least you got to be able to recognize the cylindrical coordinates answer, all right? Now that being said, it's kind of a trick question in your favor, in that if we're going to find the volume that's trapped between a surface and the XY plane, regardless of the interval, it's definitely going to be a triple integral or an integral that's evaluated, a triple integral that's evaluated to become a double integral. So we can't just dismiss that first choice out of hand, but it definitely kind of feels out of place, right? In the sense that it has some ingredient that just doesn't feel quite right. Right? But I could be wrong. Anyway, looking at the third and the fourth choices, you see that we have just r dr d thetas, and then we have some bounds for a third variable that hasn't really been stated. So a triple integral should have 3 variables accounted for in some capacity, right? So if you have 3 sets of bounds, then you should have 3 of those d whatevers, right? In cylindrical coordinates, it's dz, dr d theta. So the suspicion is that the third and fourth choices are inappropriate. They shouldn't be there. But that's more like trying to diagnose the solution to the problem without doing the problem itself. So let's just not do that. Let's dive in and see what the story is. All right, that's where this picture comes from. All right. So I'm just going to do a quick snip and bring it in. I'm going to pop it in there. Now this one's telling us that we want the volume of the solid inside the sphere but outside the cylinder. All right, so let's just take a quick look. Here's our cylinder. Just kind of focus on this part here, because it looks like this is our y-axis. Well, I actually have the negative axis over there, so it's got to be in the first octant. So really should be kind of over here. So that'll get us to the first octant. And this would be the portion of, I'm overshooting it definitely, but part of this cylinder, and I'm just going to rough that one out. Try to make it look a little nicer. All right. Let me just kind of bring this down. Yeah, it's not, definitely not perfect, but you know, something like that. You know, so we don't, this is what we don't want. We want everything beyond that. We want all this stuff. Okay. So out from center. Okay. But trying to make a three-dimensional diagram on a two-dimensional plane is always tricky. Right. So what I would want is a few pieces of information. If I'm doing this with cylindrical coordinates, I need to know, well, the height, right? Because it's r theta z to make up the coordinates, the cylindrical coordinates, but I need my bounds. I need my bounds in the xy plane. And I have two equations that I'm working off of here. I got the sphere and I got the cylinder. So let's take a look at the sphere in the xy plane. All right, that would be x squared plus y squared plus 0 squared equals 16. But we want to get it over into spherical coordinates. I'm sorry, cylindrical coordinates. We know that x squared plus y squared is the same as r squared. So that's the same as saying r squared equals 16, making r equal to 4. All right, so the extent of this figure, I'm just going to kind of sort of ballpark it. It just looks terrible. Bottom line is, I can't. All right. So just kind of pretend that this is the outer extent of the sphere that has a radius of 4. All right. Now we need the cylinder in the xy plane. All right. That one's a little easier to handle because the cylinder is defined with infinite height. So it's going to have the same xy characteristics no matter what its z value is. So x squared plus y squared equals 4. We're looking at r squared is equal to 4, which means r is equal to 2. Okay. So that's this piece here. And that actually kind of, believe it or not, is somewhat visible. Not visible enough. Next colors. All right. So what I want is everything starting here and ending here. Right? I don't want any of this stuff. Right? So I'll keep that in mind. Also, we got let's go to green here. We're starting off at 0, and I only want the first octave. All right. So 0 to pi over 2 is all I care about. All right. So no help there because each one of the choices has a 0 to pi over 2. All right. So that's one where you can kind of use the choice to your advantage. However, we could start eliminating possibilities here because, or at least a possibility, because we know that we're only living in the interval going from 2 to 4, not from 0 to 2 or anything else, you know? So we can actually get rid of this choice if we want to. All right. So I'm going to write my triple integral. It's going to go from 0 to pi over 2. Then it's going to go from 2 to 4. Now, it could be double integral, it could be triple integral. You got to kind of play that out. And actually, double checking. It's possible, I didn't even consider this, in making my wrong answers. I think I've made 2 equivalent correct answers, but we'll see. I think there's 2 right answers to this problem. Oh, no, no, no. It says it has to be a triple integral. So you can eliminate the double integral. Okay. I got to read my own question sometimes. So this one's definitely out anyway, because it says it has to be a triple integral. All right. So this is going to go from 0, z equals 0, to whatever the top part of the surface is. Now, the top part of the surface is defined as the sphere. All right. So the surface that represents the bound on the high side, x squared plus y squared plus z squared is equal to 16. This again is the same as r squared. So z squared is equal to 16 minus r squared. And then we could say that z, because I only care about the top side of it, first octant, z is equal to the square root of 16 minus r squared. So it's at this point that you pretty much have it. Okay. So you'd have a dz and an r dr d theta as your set of, or at least your order of integration. So r dz dr d theta. Okay. And so that is consistent with the second choice. Now, if we cared about the bottom half, we wanted all this stuff down here, then I would go with this one, but we don't. So let's disregard. All right. So then number 4. Find the equation of the line that represents the intersection of planes. Right. So intersection of planes is going to be represented if there is an intersection. There's the school of thought that you should sometimes try to determine if one exists to begin with. But I kind of go the route of GeoGebra on that and say, well, if you really wanted to check to see if they exist, if a solution exists, then just graph it on GeoGebra and take a look. If the planes are parallel to one another, there won't be an intersection. So that usually just jumps off the page at you, because the normal vector would be the normal vectors would be parallel to one another, right? So we're looking at, in this case, finding the intersection. That's just either substitution, or if you want to use a matrix approach, either way. But this one's kind of nice because they flat out tell you that y is equal to 3. Now I'm going to show you both techniques just so you have it. But if I take the x plus 9 times 3 plus 7z minus 22, set that equal to 0. So all I'm doing is replacing the y here with the 3. I get x squared plus 27 plus 7z minus 22 equals 0. These two can go together to give me a 5. All right. So it's really just a question of how you want to define your variables, which one is going to be your free variable. All right. So you can go either way. You can define x in terms of z, or you can define z in terms of x. It just seems like it's easier to define z in terms of x. All right. So I'm going to solve for z here. So 7z is going to be equal to 5 minus x squared. Lord only knows why I have an x squared there. I don't know. It's been a long day. I apologize. All right. So 7z equals 5 minus x is what it should have been. wouldn't have been a plane with an x squared. I don't know. So z is equal to 5
Is it
over.
5 or -5?
Say it again.
Is it 5 or -5?
It should be a
Because we
positive 5. Because 9 times 3 gives you to 27. Oh, you mean when I bring it over? Gotcha. Thank you.
yeah.
I thought you were talking about the step earlier. Yeah, good catch. Thank you. Thank you. So -5/7 minus 1/7 x. That's what z would be equal to. I mean, you could just write it as -5 minus x over 7, but put it in linear form just makes it easier. If you had to come up with a graph, it's a little easier to conceptualize. All right. So we know y is always 3. That was stated there. X is then the free variable. So we would let x be equal to t and define this thing as parametric, a linear parametric equation in terms of t. And so we could write it as f of t, r of t, whatever you want. It's a vector valued function. I'll call it f of t. The x is equal to t, the y is equal to 3, and z is equal to this. Except with a t replacing the x. All right. And so that parametric equation would define the intersection between the two planes. All right. The other approach, just without spending too much time on it, because I don't want to bore you, but I also want you to be prepared, of course. So you can do it with Desmos and some linear algebra, row reduction techniques. So you have x plus 9y plus 7z, and I'll write it as equals 22. So I'll say 4. And then y equals 3. All right. So that would be, if you stripped it down into just the coefficients, the set of coefficients 1, 9, 7, 22, 0, 1, 0, 3. So then you apply the reduced row echelon form technique, the RREF. Never actually saved it in the favorites. I got my bookmarks and I got all that stuff instant. Justin Timberlake, of course. Oh wait, bookmarks. Favorite. No, I'm still a thing. All right, I got to figure out why it's not saving here. But anyway, Desmos. Expand it. Matrix calculator. Bring it back. And then now what I'm going to do is add a bookmark. All right. Doesn't help us this semester, but. All right, so it's 2 by 4. So 1, 9, 7, 22, 0, 1, 0, 3. And then we apply the RREF on matrix A, and we get 1, 0, 7, -5, 0, 1, 0, 3. Nothing new in the second column because we already knew what y was equal to. But what this is telling us, just based off of that first, I think I said second column in the second row, that first row is telling us that x plus 7z is equal to -5, which means that x is equal to -5 minus 7z. Right, so in this case, based off of the row reduction stuff, we're letting z be the free variable. Right, in which case we would have f of t would be equal to -5, so let z equal t. -5 minus 7t, comma 3, comma t. And if you were to plot both of these over appropriate domains, you would end up with the same path. Okay? So you can get the solution either way, two different looking answers, but both equivalent. All right. So gets the job done either way. All right. The reason I show this technique is because you can't always guarantee that you're going to have a nice clean y equals 3. If you have two funky looking plane equations, then you got some work ahead of you. And so instead of doing it algebraically, you could do it using the row reduction technique. All right. And the extra caveat being that you don't have to do the actual computation. You don't have to do it by hand like in a linear algebra course. All right. So number 5, potential function for the vector field. First, we got to make sure it's conservative. All right. So we have our P's and Q's. You got to mind your P's and Q's. So partial with respect to x, that's what we're calling P, is equal to 8 minus 3x squared. I'm going to write it as y to the negative first, plus 5x to the 4th y squared. I'm going to differentiate with respect to y. All right. So the 8 goes away. -1 times -3 becomes +3, x squared y to the negative second, plus 10 x to the 4th y. Okay. So now we just got to make sure that the partial with respect to y, which we're calling q, will have itself a partial with respect to x that's equivalent. I'm going to write the x cubed over y squared as x cubed y to the negative second minus 3y squared plus 2x to the 5th y. All right. 6 goes away. I'm looking at here, again, partial with respect to x. So x cubed becomes 3x squared. So 3x squared y to the negative second. The second term goes to 0, or well, really the third term, the -3y squared, because there's no x there. And then the 2x to the 5th y is going to become 10x to the 4th y. So we have a conservative function, vector field. All right, so we're good to go there. All right. So then, in order to find a potential function, what we're going to have to do is anti-differentiate either one of them. Doesn't make a difference. Whichever one you kind of deem to be a little easier to work with. Really, like I said, it doesn't make much of a difference whatsoever. So I'll take, in this case, 3 terms compared to 2 terms, I guess. So I'll go with P. All right, so partial f with respect to x is equal to 8 minus 3x squared y to the negative first plus, for equality, plus 5x to the 4th y to the second. The differential equation, I want to get it in differential form. So partial f is equal to all this stuff with respect to x integrate both sides. Antiderivative 1 with respect to f, partial or otherwise, it's still going to give you the f. On the other side, with respect to x, I'm looking at 8x minus x cubed y to the negative first plus x to the fifth y to the second plus some constant function in terms of y. So c of y. Because that would differentiate down to 0 if you took the derivative with respect to x. Okay. But what we're going to do is not that. We're going to take the derivative of this with respect to y. So this will go to 0. The next one is going to go, well, the negative y to the negative first is going to give us an x to the third, y to the negative second, and then plus 2x to the fifth, y to the first. All right. And then we have the c prime of y. All right. So since we know the first order partial with respect to y is q, I could let me just take this whole thing down here. We have an equality relationship. I can set these two jammies equal to each other and use that to solve for c prime of y. Okay. So I'm just going to take a second to rewrite. X cubed y to the negative second plus 2x to the fifth y plus c prime of y. I mean, you can cancel on the fly if you want. I'm just showing all the extra steps. 6 plus. And almost got myself right into trouble there. And then we have minus 3y squared plus 2x to the fifth y. And so we're going to have cancellation, common terms. These two are gone. These two are gone. So that means, and so we would write this as dc dt, dc dy. And it all jammed up there. All right, so dc dy is equal to 6 minus 3y squared Gotta give myself a little bit more space. Another differential equation that can be solved by getting it into differential form first. So dc would be equal to 6 minus 3y squared dy. Integrate both sides. 1 goes to c. Now remember that c is what I talked about during the lecture. Add c on the left is really c of y, because we're about to introduce another constant of integration. So 6y minus y cubed plus c, as in an ordinary constant. All right. So now I can state finally, at long last, these problems are always a little crazy. The solution, which is all that stuff that we had before with this stuff tacked on in place of the C of Y. And if we had some kind of initial condition, then we would use that condition to figure out the value of C and get a particular solution. In this case, we can only come up with the general solution. So a lot of stuff going on with that. I don't want the video to be too long, so I'm going to stop this recording.